the terminology is very wrong, okay? Imaginary number, complex number, these are bad words because they are equally existent and real as any other number you've ever come across, okay? Just to give you a sense of perspective, let me close the door, I'm making a lot of noise. Just to give you a sense of perspective. For example, we saw how averse people were to accepting the existence of irrational numbers. And even the fact that negative numbers weren't even commonplace until, the year like 1700 or whatever. The definition of what is allowed to be a number has changed wildly. And so it's unfortunate that they don't really teach you about I, because under any mathematician's conception of what is or is not allowed to be a number, I most certainly is. And it's not seen as any more or less real or imaginary than any other number. Just to give you a sense, to the Pythagoreans, number was 1, 2, 3. Could you draw a line of, could you count, a number of rocks of that quantity? Then, of course, fractions were allowed because you could divide things into fractions, so fractions were admitted as numbers. Irrationals were eventually allowed as numbers because they figured if you can draw a line of this length, it's allowed to be a number. Of course, that's why people were so averse to negative numbers, because you can't draw a line of negative length, but then people conceptualize like, okay, negative number is just, owing you a number. And so that's not really, you have to just allow your circle of what is or is not allowed to be a number to expand. So then basically we thought, okay, if we have square roots in the, we should allow square roots of the negatives too. I is allowed to be a number. So how do we think about I? So I is fundamentally moving outside the scope of what numbers we think are. If this is what we might call the real number axis, okay, starts at 0 here, there's 1, there's 2, that goes in this way, there's -1, there's -2, goes like that way. Okay, this is the real number line. We're very familiar with this. The real number line is nice because everything on it has a point, okay? It's closed everywhere. What am I saying? Fractions, quotients, rational number line. Sorry, the rational number line, if you just had fractions on here, then there would be places where there is nothing there. For example, right here at the square root of 2, right? There's nothing here if we were just on the fractional number line, but on the real number line, everything on here is nice and closed, okay? So it's really nice. It's what allows us to do things like intermediate value theorem, real value, mean value theorem. It's got some good properties. Okay, however, I, which we've said this, if these numbers have square roots, then these ones should too, isn't here. We can't possibly represent it as a point on this real number line. We have no choice but to use a different system, and it's called the complex plane. So now, instead of numbers being points on a line, they are points in a two-dimensional space, okay? This is the real number axis. This is the imaginary axis. And so let me give you some examples of what I mean. So now, complex numbers, as we so call them, are two-part numbers. So you might write Z is a complex number. It's got a real part plus an imaginary part. Okay, this is all probably sounding very strange and very abstract. It's very unusual. So what does this mean? Let me give you some examples of complex numbers and how we can represent them on the plane. So let me give you an example. Here's a complex number, the number 1, the usual number 1 that we know and love. Here's what it looks like on the complex number plane. Let me get some colored chalk out. Here's what it looks like on the complex number plane. Okay. Yeah. There's Z equals 1. Because Z equals 1 is a complex number, of course the real numbers are contained within the complex numbers, it's just those that do not have any imaginary component. So we still get the real number line. So there's 1. How about the square root of 2? Well, it's right there, just like it was before. Okay? Everything's here. The question is, how about I, right? This thing I is up here, right here. Right? Because this is the I-axis. So here is 1I, here's 2I, here's 3I, here's etc. And then there's negative I, negative 2I, negative 3I, etc. Okay? So how about, let me just do another number just to show you what it's all about. How about if I want 1 plus I, right? What does that mean? I go 1 this way on the real part of the number, and I go 1I up this way. So it's a point sitting in space. You could draw a little arrow to it if you wanted to. Okay? So there's this right here. This dot represents the complex number 1 plus I. Okay? So that's good. So I mean, I could get arbitrarily, if I wanted negative, negative 6 minus 4i, it's not hard. You just go minus 6 out this way, minus 4 down that way. It's sitting right there. Okay? So these are, again, obviously the scale is off. But you understand what I'm saying, okay? Is that okay? Is that clear? This is complex number, okay? But now let me just show you what it means to say that I squared is equal to negative 1. So let me just kind of do a little demonstration here. So I'm going to start with z equal to 1. So that's sitting right here, right? I'll do them all in blue. Okay, so there's 1. Okay? I'm gonna multiply by I. So the pattern here is going to be multiplication by I. So I'm going to multiply by I. And what do I get? Well, 1 times I is just I. 1 times I is just I. Okay? Nothing different there. What does I look like? I looks like this. So here's what I did. I did times I, and I got a little 90-degree rotation like that. Okay? Let me multiply by I one more time. Well, then I get I times I, which is I squared, which by definition is negative 1, right? That's the definition of I. So I get negative 1 here, okay? Well, that kind of makes sense. If I went from 1 to I rotated 90 degrees. I'm now going to go from I to negative 1. That's kind of really nice, right?
So is I a distance?
Well, I is just that's like saying, is 1 a distance?
Okay.
Sure, 1 is the distance between 0 and this point on the real number line. Equally, I is the distance between 0 and the complex number line. But I is a number, right? Just like that's. Do you realize that your question is the same as saying like, is 7 a distance because 7 is over here? You know what I mean? I'm sorry, that's not minus I. Here's minus 1. So what does this mean? I squared is equal to minus 1. It means if we think of I as rotate by 90 degrees in the complex plane, right? Then yeah, I squared is minus 1. So we've now expanded our concept of number. Okay? Before number was things you can draw. Now number is, the ability to do rotations in the complex plane, for example. That's allowed to be a number. So now a 90-degree rotation, that's a number, we call it I. And it has the nice property that itself squared is negative 1. Yes? Sorry, let me just get ahead of
Okay, go
ahead.
So for example, if you're trying to find what the root of negative 7 is, that would be root of 7 times I.
Correct. You're
so
exactly
I
right.
just solely defines the root of negative 1.
That's correct. That's exactly right. Yeah.
If you multiplied 1, like you by multiplying by I, you rotated 90. So can you multiply by like half I and rotate 45?
Yes, you're exactly right. Yeah, multiplication by I over 2 would get you. Actually, let me think about that for a second. Would it? No, it would not. I'm sorry. That's not correct. Okay, that was a mistake. Because multiplication by I over 2 is the same as multiplication by I then multiplication by a half. So multiplication by I over 2 would bring you here, and then you would go divide by half, so you'd go half, so you'd be here. So there's I over 2. Do you know what I'm saying? Right? Yeah? That's good.
Okay,
So let me just give me 1 second. I'm just going to do this one more time. Okay. So I'm just multiply by I one more time. This is z is equal to minus I. Okay, exactly as expected, right? We rotate by 90 degrees again. Get here to minus I. Let me multiply by one more time. This is going to be minus I times I, which is minus I squared, minus 1, which is positive 1. And we're back to where we started. So I just want to point out something very quickly here. The pattern is this, okay? The pattern goes 1I minus 1 minus I. 1I minus 1 minus I. Okay? So it goes positive, positive, negative, negative, positive, positive, negative, negative. Is that okay? And it alternates between being 1 and being I. Okay? So this is very important. And I'm just going to write the pattern right here, because I'm just going to write it right here. So 1I, negative 1, negative I. 1I, negative 1, negative I, dot, dot, dot. Okay, so this is the pattern. I'm getting like jitters just thinking about what's about to happen. It's so exciting. Okay. It alternates between 1 and I, alternates between 2 negative and 2 positive. Okay. It's crazy. Okay. What's that?
Is it a sequence?
Yeah, we could think of this as a sequence if we wanted to. Sure. Now it's a sequence. It's now a
I
sequence,
feel
right?
I feel better now.
But this is just, I mean, if you just look at it, it's just what rotation by 90 degrees is, right? Bailey?
Oh, okay. So why did you pick the root of -1 to base the entire imaginary number line on?
Well, you could theoretically pick the root of any negative number, but say you pick the root of -2. It would then have the property that squaring itself, right? So if you let, say, you let I equal the square root of -2, for example, okay? Then you look at this thing and you go, well then, I squared is equal to -2. So if I start with 1, and then I multiply by I, okay? So I go from 1 to I, right? And then I multiply by I again, and I get -2, I'm now growing. Do you know what I'm saying? I'm now here at -2. And then if I multiply by I again, I get -2I. And if I multiply by I again, I get 2. Ooh, that's not so nice. This gives you this very, very nice property.
Because it's the multiplicative identity.
Because that's exactly right, because 1 is the multiplicative identity. Similarly, I is the identity, so to speak, of the complex numbers, right? It just forms the foundation for the complex numbers. It's the basis unit, right? 0 is still 0. I is like 1. For very clear reasons, yes?
What do we use the imaginary numbers for?
So imaginary numbers are everywhere, right? So what's that? That's one thing. But basically, in the future, in a few weeks, we'll see that most of the functions in the real world are not functions of one variable, right? They can be multi-valued functions. Sometimes it's nice to represent numbers as complex numbers. For example, say you've got a function, that takes in the position on a. Say you've got I'm making this up, but say you've got a sheet of paper and you want it's got a non-uniform temperature distribution, and you want to find out what the temperature is as a function of the position. So you set up some axes and you say, at this point, what is the temperature, right? Or at this point, what is the temperature? And there's a function for that, right? So you plug in 2 numbers and it gives you the answer. Sometimes it's more convenient, instead of saying, what is f of x comma y, that is, plug in 2 values and give me an answer. Sometimes it's more convenient just to say f of z. Plug in a complex number, which is itself has 2 components, but it's nicely packaged as one thing with this I thing. But also there are countless applications to, most notably, physics. Physics would be no